Okay, but why did that question ask for the binding energy per nucleon? Why did it care about that? Why not just ask for the binding energy? Because it turns out that if you look at all the isotopes of all the different nuclei and you plot how many nucleons they've got on this axis and their binding energy per nucleon on that axis, you get this very clear and important pattern. So what's going on there? We're going to think about what's happening with the energy when a nuclear reaction takes place. The first thing that happens is that the nuclei you have beforehand, you need to pull them apart into their constituent parts. And how much energy does that take? Well, that's the total binding energy before. So you're going to have to spend this much energy to pull everything apart into its pieces. And then when all the new stuff forms, when it sticks all back together again, you're going to get this much energy given out. So let's call that, so E1 is how much energy it took to pull everything apart, and then E2 is how much energy came out when all of your particles stuck together again in a new arrangement. Now remember that the total binding energy after is equal to, in size, to what this energy was that was released. So if this number is bigger than that number, then overall energy is released and the nuclear reaction is exothermic. But if this number is smaller than that number, then overall energy was needed for that reaction to happen, and so it's called an endothermic reaction. Now, both types of nuclear reaction can happen. It's just that if we want one of these to happen, we have to supply, it's going to take energy from its surroundings for it to happen. But this one here, it's going to release energy overall. So this can happen without needing to take energy from its surroundings. So if you're thinking of, say, alpha decay or a fission reaction or a fusion reaction, they're all going to be exothermic, total binding energy after bigger than the total binding energy before. And that is what lies behind the pattern on this graph. Remember that baryon number has to be conserved in all nuclear reactions, and that means that the total number of nucleons has to stay the same. So if you want the total binding energy after to be bigger than the total binding energy before, then you need each nucleon to end up with more binding energy after than it had before. And that means that whatever you've got after needs to have moved this way from what you had before. So reactants, products, they're moving towards higher binding energies per nucleon. And so that means that for any exothermic reaction, any nuclear reaction that gives out energy overall, its products will be closer to the peak there than its reactants were. And then right at that peak there, you've got iron 56. Which is the most stable nucleus. So once you become iron 56, you don't do any more exothermic nuclear reactions. And this is the answer to something that I think can seem very puzzling when you're further down the school. How is it that fission and fusion both give out energy? They're both exothermic reactions. How can that be when fission involves very large nuclei falling apart into smaller nuclei, and fusion involves small nuclei sticking together to form larger ones? And the answer is binding energy per nucleon. Fission reactions are out here moving that way, and fusion reactions are down here moving this way, and that's why they're both giving out energy overall. It also shows you why fusion is so desirable compared to fission, because if you look at, in fission, you might be moving from, say, here, even if your reactants are there and your products are all the way up there, the actual change in height there, the change in overall binding energy per nucleon isn't that big. I mean, I know you've got lots of nucleons, but still not that big. Whereas if you look at fusion, you're getting these huge jumps in binding energy per nucleon when things stick together, and that's why we're trying really hard to do fusion at the moment. Okay, have a little go at this question. I know we've sort of covered most of it, but have a little go at that now. Okay, so estimate the value of the nucleon number of the most stable isotope. So we know it's 56, and if you put 56, that's totally fine. But they'd let you have sort of anything on that flat patch. So anything from like 50 to 60, I think, would get you it there. And then explain why. Must use the graph to explain why molybdenum, not sure what that one is, 100, why can it not produce energy by fusion? Well, if its nucleon number's 100, it's there. Now, to do fusion, that means some of them have got to stick together to form bigger things, which would mean moving that way down the curve. So we're going to say that it would, if it did fusion, then the things it turned into, the products, would have less binding energy per nucleon than the thing it started out as. And that means it's an endothermic reaction, not an exothermic reaction. So it can happen, it's just it would need to take in energy in order to happen, whereas an exothermic reaction gives out energy overall when it takes place.